Hey everyone, welcome back. We're always on the lookout for those papers that really push the boundaries, and today we've got one that tackles a visual challenge I think we can all relate to. Getting those really sharp close-up views of 3D scenes, the kind that just makes you feel like you're right there. And 3D Gaussian Splatting, 3D GS has really shaken things up in the rendering world, right? Real-time, high quality, the whole package. But as we go further with any tech, we always find new, tougher problems to solve. And in this case, it's nailing those close-ups. Like, how do we keep that same visual fidelity when we zoom way in?
You hit the nail on the head. 3D GS has been a revolution for novel view synthesis, no doubt. It's fast, it creates great results overall, but it definitely stumbles when you ask it to render images from viewpoints that are much closer than what it was trained on. It's like, imagine you're teaching a model to understand a scene from a certain distance, right? Specific angle, specific amount of detail visible, then boom, you suddenly switch it up and demand this totally different view, like a super close-up. Well, the poor model might not have the information it needs to keep things looking crisp and accurate. It's almost like trying to figure out all the tiny brushstrokes in a painting when you've only ever seen it from across a giant room. You get this blurry, maybe distorted image, just not the full picture.
Right, yeah, totally. It's like trying to make out the individual leaves on a tree when you're miles away. You just can't get that level of detail. So today, we're going deep on a paper that dives right into this close-up rendering problem in 3D GS. And the approach they take, I gotta say, is pretty ingenious. They use a progressive refinement technique for the 3D GS model, and the kicker is they do it using data that the model itself helps generate, all with a little help from a 3D-aware generative model. Sound complicated? Well, we'll break it down for you.
Absolutely, we will. So the title of this paper is a mouthful, but it really captures the essence of their work. Close-up GS, enhancing close-up view synthesis in 3D Gaussian splatting with progressive self-training. And right off the bat, they lay out the core issue with rendering close-ups using 3D GS. See, when you change viewpoints drastically like that, you're essentially asking the model to generalize to a scenario that's outside of what it learned during training. They call these out-of-distribution viewpoints, and they're a major headache for any model. What happens is the visual quality tends to drop because the model is struggling to make accurate predictions. And when you zoom in, all those little details that might have looked fine from afar become way more important, right? Suddenly you're noticing inconsistencies, occlusion, things that weren't even visible before.
And to really drive this point home, they included a figure 1 in the paper, that visually shows how much better their method is compared to what's out there. They tested at different zoom levels, 3x closer, 9x closer, even a crazy 27x closer. And the difference in quality, especially at those extreme close-ups, is just remarkable. Not just as a small improvement, it's a pretty big jump in what we can achieve.
I agree. Their method, which they call close-up GS, uses this idea of progressive self-training to tackle these close-up rendering issues. It's a step-by-step process where they refine the 3D GS model's understanding of the scene, and each step gets us closer and closer to those high-quality close-ups.
Okay, I'm hooked. Let's get into the specifics of their approach. Walk us through exactly how they do this.
Sure. So they start by defining the problem in section 4.1. They describe it like this. You've got this pre-trained 3D GS model, right? It's learned from a bunch of views taken from a certain distance. The goal is to take that model and update it so it can create really nice images when we move the camera much closer to a specific object in the scene.
Got it. So we're not talking about, like, gathering a whole new data set of close-up images and training a brand new model from scratch. That would be a whole other beast.
Yeah.
Here, we're being smart and adapting an existing model to handle this new challenge.
Exactly. And they remind us about those two big challenges we mentioned before. First one, those pesky light rays. When you're up close to something, the way light hits it is totally different than when you're far away. And those differences can really mess up the rendering. It's like trying to mix a color you've never seen before. You just don't have the right recipe. And this problem is even worse in areas that were hidden in the original distant views, but suddenly pop up when you zoom in.
Yeah, that makes sense. It's like the model has no clue what's behind that object because it's never seen it before.
Precisely. And the second challenge is all about those fine details. Think textures, intricate shapes. When you're far away, you might capture them at a lower resolution. But zoom in, and suddenly you need much more information to make them look realistic. If the model hasn't seen those details in its training data, the close-up is going to look blurry or just dot off.
All right, so the problems are crystal clear. Now, how does close-up GS solve them? They talk about this enhancement with generative models thing, right?
Yep, that's the heart of their approach. It's all in section 4.2. They introduced this 3D-aware generative model called C3D. You can think of C3D as an expert in 3D visuals. It's been trained on tons of data, and it has this amazing ability to kind of fill in the gaps when we move into those close-up views.
So the 3DGS model takes a stab at rendering the close-up, and then C3D steps in to make things better.
You got it. But first, they do something clever. They use a technique to identify the parts of the initial rendering that are reliable, meaning they match up with the original training data. This creates a mask, which basically tells C3D, hey, these areas are probably good, but these other areas might be a bit wonky because we're extrapolating.
So C3D focuses on those wonky areas.
Exactly. It takes multiple inputs, a set of reference views, the initial rendering from 3DGS, and that reliability mask. Then it uses all this info to refine the new view. It basically fills in details in those masked areas, like a painter adding in the fine brushstrokes. They even mention using super resolution techniques to make those details extra sharp.
Cool. So C3D is like a detail-oriented artist using its knowledge of 3D scenes and the rough sketch from 3DGS to create a more finished, polished piece. And then this refined image is used to train the 3DGS model even further, right?
You're catching on quick. This is the core of their self-training approach. The refined image, with its hopefully more accurate and detailed close-up information, becomes new training data for the 3DGS model. It's like the model is learning from its own improved homework thanks to C3D's expert guidance.
But they do mention some challenges with this process, don't they?
They do. Two main things to watch out for. First, C3D needs good references. The reference views it gets have to show the object from similar angles to the new close-up view. If the references aren't helpful, C3D can only do so much. Second, they stress the importance of consistency across all views. As they update the model, they have to make sure it's not learning conflicting things. You don't want it to learn something new from the close-up that contradicts what it already knows from the far-away views. That could cause all sorts of rendering weirdness.
Right. Consistency is key. So how do they make sure they have good references and keep things consistent during this whole process?
This is where their progressive model update scheme comes into play, and it's a clever solution. They explain it in section 4.3. They gradually expand what they call the trust region of the model over multiple rounds. Think of it as the model's comfort zone. They start with those faraway views where the model already performs well, and then slowly but surely they push the boundaries closer to the target object. Figure 2 in the paper is a great visual of this expansion process.
And each expansion round has 4 steps, right?
You got it. The first step is to select anchor views, which is explained in detail in 4.3.1. Each round, they pick a handful of views from the current set of known views. But this isn't just a random pick. They choose views that show as much of the target object as possible, while also making sure the views aren't too similar to each other. They even introduce this idea of frontier views, virtual cameras placed closer to the object to help them figure out if they're covering all the important angles. The whole process is set up as an optimization problem, mathematically balancing coverage with similarity.
So these anchor views become the trusted guides for refining the closer views in the next steps.
Exactly. They're the references that C3D will rely on. The second step, described in 4.3.2, is to select to be updated views. They start by randomly picking a bunch of virtual camera positions between the known views and those closer frontier views. Then they narrow it down to a smaller set of to be updated views using a similar selection process as before. These selected views are like the stepping stones, connecting those well-understood faraway views to the more challenging close-ups. They're all about making sure the new views created by C3D fit in with the overall 3D structure learned by the model.
So instead of one big leap, they're guiding the model closer, step by careful step.
Right on. The third step, render and refinement, 4.3.3, is where the magic happens. They render those to-be-updated views using the current 3DGS model. Then they take those initial renderings, along with those carefully chosen anchor views, and feed them to C3D. C3D refines these views, adding details and making them look more realistic. They also mention they might use an extra image enhancement model here to really boost the quality. These refined images become the new training data, and the to-be-updated views are added to the set of known views for future rounds.
It's like the model is constantly learning from its own increasingly impressive work.
Exactly. And the final step, Gaussian Splatting fine-tuning, 4.3.4, is all about integrating those new images into the training data. But they don't just throw them in willy-nilly. They use those reliable pixels from the refinement process as constraints, making sure the new ATHO doesn't clash with what the model already knows. And they do this cool thing. They add more Gaussian primitives when those to-be-updated views are much closer to the object. This lets the model capture all those extra details that become visible at close range.
Makes sense. It's like you need more pixels in a photo to capture the details of something small.
That's a great analogy. So that's the progressive update scheme. It's a multi-step process where they pick specific views, enhance them with C3D and some clever tricks, and then fine-tune the 3D model, all while making sure things stay consistent.
Impressive. Now, how did they test this whole thing? What experiments did they do to prove close-up GS actually works?
In Section 5, they get into their experiments. They realized that most existing data sets weren't ideal for evaluating close-up views, so they built their own, which they call the Extracted LERF dataset. They took scenes from the larger LERF dataset that had both far-away and close-up views of the same objects. They used the far-away views to train their models and the close-up views to test how well their method worked. They could then use standard metrics like PSNR, SMUM, and LPIPS to measure the quality.
And what about those super extreme close-ups, the ones that are really tough to get real-world data for?
For those cases, they focused on specific objects within scenes from the LLFF dataset, testing at 3x, 9x, and 27x closer. Since getting perfect ground truth for these extreme close-ups is almost impossible, they came up with two new ways to measure quality. First, they used the Dino score, which basically tells you how similar the generated close-up is to the training view that shows the object best. And second, they used Meta-IQA, a metric that measures the overall visual quality of an image without needing a reference.
So they used a mix of established metrics and some clever new ones to cover all the bases. What about the nitty-gritty details of their experiments? What did they actually do?
Okay, so they ran a 3-round progressive update on the LLFF dataset. In each round, they got closer to the object 3x, then 9x, then 27x. Each round, they carefully picked 5 anchor views and 8 to be updated views. For the single-round LERF experiment, they cleverly used the testing views themselves as the frontier views. As their baseline, they used a standard 2D Gaussian Splatting model trained for 30,000 iterations. In each close-up GS round, they fine-tuned the 3D GS model for 5,000 iterations, and they only used Gaussian densification when moving to 3x closer views. Oh, and all their experiments were run on those powerful NVIDIA 4090 GPUs.
So a very well-defined setup with specific parameters and a strong baseline. What were the results? Did close-up GS live up to the hype?
The results are pretty impressive. On the extracted LERF dataset, where they did that single-round update to 3x closer, Table 1 shows that close-up GS significantly outperformed a whole bunch of other methods. We're talking NERF variations, standard 3D GS, 2D GS, even a previous pseudo-labeling technique specifically designed for close-ups. And Figure 3 shows the visual comparisons, and you can clearly see how close-up GS reduces artifacts and creates more complete and accurate close-ups.
Okay, cool. And what about those extreme close-ups on LLFF, those 9x and 27x zooms?
Figure 4 has those results, and it's pretty striking. As the close-up gets more extreme, the other methods really start to fall apart. They get blurry, distorted, just messy. The close-up GS holds up really well. It keeps the details sharp and the image consistent. Table 2 backs this up, showing that close-up GS wins by a large margin in the Meta-IQA score at the 27x scale. That means it's creating much more visually pleasing images at those crazy close-ups.
Yeah, those visuals in Figure 4 are super convincing. You can really see the difference.
Right. And they didn't stop there. To really understand what's making their method work, they did these in-depth ablation studies, which they discuss in Section 5.4. They tested different refinement strategies with C3D, their view selection process, the progressive updates, and the Gaussian densification.
So they really broke down their method to see what makes it tick. What were the key takeaways from those studies?
Well, Table 3 shows that just using C3D on its own to render close-ups wasn't as good as their full method. That suggests those inconsistencies with the underlying 3D geometry we talked about. The best results came from combining the refined output from C3D with the reliable pixels from the initial 3D GS rendering, and then enhancing that combined image even further. It really shows the power of combining the generative model's creativity with the geometric knowledge from the original model.
It's about finding that sweet spot, isn't it?
Yeah, totally. And Figure 5 shows how crucial their view selection strategy is. By picking the right views, they get better results, higher PSNR, with fewer views and less computational work. And finally, by comparing their full method to versions without progressive updates or densification in Table 2 and Figure 7, they clearly demonstrate that both of those components are essential for those high-quality close-ups. You can't just jump to a 27x close-up and expect good results, and you got to give the model the tools it needs to handle all that extra detail.
So every piece of their method is important. Now, let's zoom out a bit. How does this research fit into the broader landscape of machine learning and computer vision?
Section 2 gives a nice overview of related work. We've seen this progression from those early implicit radiance field methods like NERF, which were amazing but slow, to faster, more efficient explicit representations like 3D-GS. But even these faster methods have trouble with what they call unconventional conditions, things like limited training data or those tricky out-of-distribution viewpoints we've been talking about.
And generative models are playing a bigger role now, right? Especially these diffusion models. They're being used more and more to improve 3D generation and novel view synthesis.
Absolutely. There's a lot of excitement around using these models like C3D, which can learn so much from 2D images, but combining them with explicit 3D representations like 3D-GS is tricky. Getting that geometric consistency right is still a big challenge.
So close-up GS is a great example of bridging that gap, right? Using the generative model's power to boost details while respecting the 3D structure from 3D-GS.
Precisely. They wrap up by highlighting a few key takeaways. Their progressive training works well, C3D adds crucial detail, their view selection is both effective and efficient, using reliable pixels keeps things consistent, densification is a must for close-ups, and they've developed new metrics specifically for this problem.
Those are some solid takeaways. Now let's put on our Future of Research hats. In our Novel Notions segment, we like to brainstorm a bit. What kind of crazy, but maybe not so crazy, ideas could this research lead to?
Okay, here's one. What about adaptive trust region expansion with uncertainty estimation? Instead of those fixed steps, what if the 3D-GS model could tell us how confident it is about rendering certain views? The trust region could then expand faster in areas where the model feels good and slower in areas where it's uncertain. Maybe it could even focus its learning on those tougher spots.
Whoa, the model becomes self-aware, learning where it needs to improve the most. How could we actually do that?
There's a bunch of research on uncertainty estimation in neural networks, using things like Bayesian neural networks or ensembles. We could adapt those techniques for 3D-GS, giving us a way to measure how sure the model is about its outputs. Then we could use that uncertainty to guide the selection of those frontier views and adjust how the model learns.
So we'd get a more efficient, targeted training process, especially for those complex scenes. That could be huge for things like robotics, where the system needs to quickly focus on specific objects.
Exactly. It ties into the whole field of active learning, where the model gets to choose what it wants to learn. Okay, ready for another idea? Let's go even further with close-ups. Integrating multimodal priors for extreme close-ups. Close-up GS uses the visual knowledge from C3D. But what if we zoom in even more, like 27x or beyond? C3D might struggle there because the original images just don't have that level of detail. So we could bring in other types of data, like text descriptions, semantic maps, or even material properties to guide C3D.
Whoa, so we're talking about using language or other info to help the model imagine those extreme close-ups.
Yep, imagine trying to render a super close-up of a thread in a tapestry, but the original photos aren't detailed enough. Well, if you have a text description of the thread's weave, color, and texture, that could be super helpful for creating a realistic close-up that goes beyond what's in the images. This links back to research on vision language models and neural rendering with semantic control.
That's a really cool idea,
Yeah.
using language to enhance visual rendering. But wouldn't it be tough to make sure everything stays consistent?
Absolutely, that's the challenge. We'd have to make sure the language aligns perfectly with the visuals from 3D-GS and the generated close-up. But if we can crack that, imagine the possibilities. Visualizing microscopic structures, recreating historical objects in incredible detail.
Those are some mind-blowing possibilities. And just to be clear, these are just brainstorming ideas for future research.
Exactly. It's about getting those creative juices flowing.
This has been an amazing deep dive into the world of close-up GS. Their approach is a big step forward in solving this tough challenge of getting those high-fidelity close-up views in 3D-GS. It opens up tons of exciting applications.
Agreed. It's a big win for anyone working on realistic novel view synthesis.
We'll be sure to link to the full paper in the show notes so you can check it out yourself. And this leaves us with a big question. What's next for this field? What crazy new ideas will allow us to create even more detailed and realistic virtual environments, maybe even going beyond what we can see with our own eyes? It's going to be an exciting ride. Thanks for joining us on this deep dive.